Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. We're going to continue our lecture on thermodynamics and talk about today about Hess's Law. Here are all of the things that you will need to know for this video. So, these two, if you flip an equation, you change the sign of the enthalpy. So if it's positive, you'll change it to negative. We'll talk about that more later. If you're multiplying coefficients, you're going to multiply the enthalpy by the same factor that you multiply the coefficients. All elements in our standard states at 298 Kelvin and 1.0 times 10 pascals have a standard enthalpy of 0. So oxygen, carbon, hydrogen, all of those, the standard enthalpy of those is going to be 0. Enthalpy of formation makes 1 mole, and enthalpy of combustion burns 1 mole. We'll talk about those more later. And if I'm going to calculate the enthalpy of a reaction, know that to do that, you're going to just take the enthalpy of the products and minus the enthalpy of the reactants. And lastly, in an enthalpy cycle, all the clockwise arrows should equal all the counterclockwise arrows. Hopefully those will make more sense when we do more examples. Now here's something that you should already know. Reactants and products are shown here in this energy diagram. The products are lower than the reactants. We know this is going to be exothermic, it's going to release energy. But we have this energy barrier here, or this activation energy, EA. This is the amount of energy needed to be overcome in order to start a reaction. You might see this with like a matchstick. The match itself doesn't just combust. You actually need to put in a little bit of energy before it's going to release a large amount of energy. And you can do that by putting friction on the match, maybe by rubbing it against a matchbox. But activation energy, energy needed to overcome in order for a reaction to start. And we can lower this activation energy by adding a catalyst. So let's do some problems. Write an equation for the standard enthalpy of formation of nitric acid. Here's nitric acid. And we need to write down an equation on how to form nitric acid. So if we take hydrogen, nitrogen, and oxygen, we can make nitric acid. If you remember, enthalpy of formation is always going to make 1 mole. So we need to change these subscripts so that they make actually 1 mole. Also, don't forget your state symbols. You will lose a point if you don't. Or if you do. And these are the states at STP. So hydrogen, nitrogen, and oxygen are all gases. Nitric acid is a liquid. Okay, let's do a similar problem for the combustion, this time of methanol. Now, in this one, you're not making 1 mole, you are burning 1 mole. Here's methanol, and we're going to burn it by mixing it with oxygen to make carbon dioxide and water. Again, I am burning 1 mole, so these other coefficients have to change so that I am burning 1 mole. And again, don't forget the state symbols at STP. Methanol is liquid, gas, liquid. Calculate the enthalpy of combustion of butane. So notice here we're doing the enthalpy of combustion. Notice we are burning 1 mole. Now, they've given us the enthalpy values of our various components of a reaction, and to figure this out, I'm going to have to do products minus reactants. So let's take a look. My products are carbon dioxide and water, so I'm going to take the coefficient 4 times the enthalpy of formation, because it's kilojoules per mole, so it's 383 times 4, and I'm going to add it with the 5 times the 285 for water. Those are my products, and I'm going to subtract the reactants, C4H10, minus 127. So you might think that, we didn't give you the enthalpy of formation for oxygen, but if you remember, elements, just carbon, oxygen, have an enthalpy of formation of 0, so we did not include it in here. And so when we do this algebra, we get 2875. Calculate HF, or the heat of formation, for enthalpy of formation, for ethanol. Okay, and they gave us these heat of formation, heat of combustion values. So here is how, here's ethanol, F for 2 carbons, with an alcohol group at the end. Here is the equation for the enthalpy of formation of ethanol. Now notice, they did not give me the values for these. And so I can't really figure out the enthalpy of formation for this. And so I kind of have to take it, add a bunch of equations together to get this full equation. So let's take a look at what they gave us. They gave us the formation of carbon dioxide, okay, and they gave us a value for that. So remember, I'm going to form 1 mole of carbon dioxide for formation. So I've got my balance equation here, okay. I'm going to combust hydrogen here, okay, so I'm going to mix it with oxygen to make water. And lastly, I'm going to combust ethanol. And when I combust ethanol, remember, in combustion, you're burning 1 mole. And this is what I get. Okay? And so we are going to go, you're going to do this on here. Okay. And so the heat of formation of this is 393. The heat of combustion of this is 285. And the heat of combustion of this is going to be -1371. Now, the strategy for this is I have to rearrange, these equations, these 3 equations, so that when I add them all up, they look like this equation at the top here. And so that's what I have to do. Now, I don't see any carbon dioxide on here, and so I'm going to have to get rid of that. Okay, and I also noticed that my ethanol is on this side, so what we're going to do is we're going to flip this one. So we're going to take the reactants and flip them with the products like this. Now when I do that, I actually change the sign of my, I actually change the sign of my enthalpy value. Hopefully you guys can see that. And so this is now going to be positive 1,371 because I flipped these. I'm going to have to double all of these. And so, let's just copy this 2 here. I'm going to have to double all of these. And so, I'm going to have 2 C's, 2 of these O's, and 2 of these carbon dioxides. And let's see, I've got 3 waters here, and so I'm going to have to triple this one. Let's give ourselves some room here. So I'm going to have to triple this one. And triple this. If I triple that, that will be 3/2. Alright, let's see. And then by doubling this one, I also double this value. So we're going to double this one. And since I tripled this one, I'm also going to triple the enthalpy values for this equation. So let's take a look if these 3 equations add up to my overall equation up here. So I've got 2 C's. I've got 3 H's. Now this CO2 here is going to cancel out with this 2 CO2 here. And these 3 waters are going to cancel out with these 3 waters. Okay. I'm going to bring down a little arrow here. I've got methanol on this side. Now let's see, this is 2, 3, 3.5 minus the 3 oxygens there, and so that does give me my oxygens there. So a little messy, but we can see that all of these add up. And so what I need to do now is I need to calculate the enthalpy, or the enthalpy of formation here. And when I do that, I do the products minus the reactants. And so I get a value of about 273.4. Okay, last thing we have to talk about is enthalpy cycles. So here are different enthalpy cycles, kind of like the previous problem where we can have a problem, we have different ways to achieve those reactions. Now this might look a little crazy, but if we assign enthalpy values for here, let's just say 5, so this one maybe 3, this one's 7, make this one -2. Okay. All of the clockwise arrows are gonna need to equal all of the counterclockwise arrows. So if we want to figure out the enthalpy of formation of B to F, then I know that these have to equal these. And so if I do this, this is going to be 5 plus -3 plus 7 should equal -2 plus the enthalpy of formation that we get there. And then so this is 9 equals, so this needs to be the enthalpy of formation needs to be 11.